We are going to wrap things up today regarding steady state sinusoidal power analysis. I didn't get quite as far into, so we have a little bit more of that material to do. The biggest part of which is a concept which is called power factor. And power factor leads into what today's lecture topic was supposed to be, power factor correction. So let's start by defining what the power factor is. So power factor is a measure of efficiency in a steady state sinusoidal system. Okay. So mathematically, our power factor is defined as the ratio of the average power P divided by our apparent power S, and this comes out to be cosine of our power factor angle theta S. P watts is what we as a consumer pay for when we pay our utility bill. Okay. S, or really the magnitude of S, our apparent power, measured in volt amperes, is what the electrical utility generates, okay? And it costs them money to generate power, either in the form of buying coal and things like that for a coal-fired power plant, or just in the infrastructure cost of being able to transmit power over distances. So the utility company wants your power factor to be as close to 1 as possible, which would be 100% efficiency. Everything they generate is being consumed and used by the consumer. But whenever there are inductors and capacitors in systems, our power factor becomes less than 1, and we'll talk about that in a little bit. And so we have some amount of inefficiency in as much as some of the electricity or the power that was generated by the utility wounds up getting sent back to them during the half cycle where that would occur. Okay. So because the power factor is based on a cosine function, the maximum value that it can ever have is 1. Okay, so we're going to talk our way through some various different angles here, right? So if theta S, let's start with positive 90 degrees, right? So if theta S is positive 90 degrees, then our power factor is equal to 0, which means we're operating at 0% efficiency. Now recall that theta S, our power factor angle, is equal to theta V minus theta I. We know a specific condition where theta V minus theta I is going to equal to 90, and that's whenever we have a pure inductance. So if theta S is equal to 90 degrees, we know that our load is purely inductive. And so I'm going to say R is equal to 0, and X, our reactance, will be greater than 0. If 0 degrees is less than theta S is less than 90 degrees, then our power factor is going to be somewhere between 0 and 1. This is the case for an inductive load where R is greater than 0 and our reactance is greater than 0. And in these situations, we call this power factor because the current is lagging the voltage by some particular phase angle, and that phase angle depends on how much resistance and how much positive reactance we have. If theta S is exactly equal to 0 degrees, then our power factor is exactly 1, which means we have a purely resistive load. Where R is greater than 0 and X is equal to 0. You may see a power factor of 1 referred to as a unity power factor. If negative 90 degrees, our power factor will range from 0 to 1. And here we have a capacitive load where our resistance is greater than 0 and our reactance is negative. We call this situation a leading power factor because the current phase angle leads the voltage phase angle. And then if theta S is equal to negative 90, capacitive load, where R is equal to 0 and X. If we look at all the angles that we have right here, these all lie in quadrants 1 and 4. Realistically, we could have angles that are ranging, between 90 and 180, and between negative 90 and negative 180. But those would require us to have negative amounts of resistance. So we're not really going to tackle that in circuits 1. Okay. All right, so let's see. So we've talked about power factor here a little bit. So let's look at an example here. And this will be our segue into power factor correction as well. So let's say that we have a system. So over here on the left-hand side, I'm going to have a voltage source. This might represent the terminals of a transformer at an industrial site. And just for the sake of argument, let's say that this is 400 angle 0 degrees volts RMS. And then here we have an impedance, which I'm going to call ZW. This is what's going to be known as a line impedance. So it represents the characteristic impedance of transmission lines. This is typically pretty small and slightly inductive. So let's call this 0.01 plus J 0.05 ohms. And then we're going to have another impedance here, and I'm going to call this Z sub M. It's going to represent the impedance of a motor. So practically all electric motors also represent inductive loads. In fact, you can generally say that if it moves and it runs on AC electricity, it's going to show up as an inductive load. The characteristic impedance of 8 plus J2 ohms. What I want us to figure out is at what power factor does supply power. So just to be clear here, I'm going to do this in blue. This is just reminding you of our relationships. Our power factor is equal to the ratio of the average power to the apparent power, and it is also equal to the cosine of theta s. And just as another quick reminder here, theta s is equal to theta v minus theta I. So for a problem like this, if I wanted to calculate the power factor at which the source is supplying power, I personally would choose to determine the complex power supplied by the source and then use the polar representation of that complex power to give me my power factor angle, and I'll simply take the cosine of that in order to determine my power factor. So how are we going to find the complex power supplied by our voltage source? Anybody have any thoughts? So let's break this down. What two pieces of information do we need in order to calculate any complex power?
Real and imaginary part?
What's the equation for complex power?
Current times resistance. It's kind of the same as resistive power, like regular power, right?
We talked about complex power at length last Tuesday. Look at your notes. I gave you a whole bunch of equations, and then I told you one is really important because all of the other ones can be gleaned from that. I want the really important one.
I'm pulling it up. It's a long one, yeah.
Oh, real short.
Oh. Complex power is bar S equals tilde V times tilde I, the conjugate.
Absolutely right.
Okay.
So we are going to need to know the voltage drop across our source, the RMS voltage drop across our source, and the RMS current flowing into the negative polarity terminal, because I'm asking for supplied power. Okay. So I feel pretty strongly that the voltage drop across our source is 400 angle 0 degrees, because I literally told you that's what it is. How are we going to find that current?
We need or ZEQ.
Okay. So what would you do with ZEQ if you had it?
I would take V and divide it by ZEQ. I would take V tilde and then divide it by ZEQ.
Absolutely. Okay. So 400 angle 0 degrees volts RMS divided by 8.01 plus J 2.05. Because those impedances are just in series, that's a pretty straightforward equivalent impedance. So I'm okay with that. So 400 divided by 8.01 plus 2.05 I gives me 48. Sorry. 0.378 with an angle of negative 14.356 degrees amps RMS. Our complex power then is the voltage times the conjugate of the current. So that's going to look like 400 angle 0 degrees volts RMS times 48.378 angle positive 14.356 degrees amps RMS. And if I throw that into my calculator real quick, I get 19,351.324 with an angle of positive 14.356 degrees. And this would be in volt amperes. In rectangular form, this looks like 18,747.093 plus J 4797.945 volt amperes. So because I'm trying to find my power factor, I'm simply going to take my power factor angle from the polar form representation. Okay. So my power factor at which my voltage source supplies power will be the cosine of 14.356 degrees. Which I get to be 0.969. Is this power factor leading or lagging?
It is lagging. And I say that because I get 400 angle 0 degrees. And because 0.969 is greater than 0, it's lagging.
So we can tell that it is lagging. Let's scroll up here. Lagging power factors occur when our power factor angle is between 0 and positive 90 degrees. So effectively, if our angle is positive, we have a lagging power factor. If our angle is negative, we have a leading power factor. It is literally that simple.
Okay.
So leading power factor means positive angle, leading power factor means negative angle, lagging power factor means positive angle. This system is operating at an efficiency of about 96.9%, okay, or power factor of 0.969. So this seems high, but may actually be too low for your utility. An electrical utility, depending on which utility it is, they have different thresholds that they're looking for. So for some utilities, they're looking for a power factor of 0.975 or higher. Others are looking for a power factor of 0.95 or higher. And if you don't hit this power factor, they're going to fine you. So let's say, for instance, that we wanted to get a power factor of 0.975 out of this system. What could we do? Well, what we would employ would be a technique called power factor correction. Okay. So let's talk a little bit about this, and then we'll revisit this example problem. So let's say that I have a situation much like the problem that we just worked. I'm drawing a power triangle here. So my real axis is the horizontal axis, my imaginary axis is the vertical axis, and let's make this purple. I have something operating at a lagging power factor. And the reason why I'm deriving all of this with respect to a lagging power factor is because the overwhelming majority of the time, we're going to be dealing with lagging power factors because of the ubiquitousness of induction motors in society and even in our homes. Our house, our inductive loads are literally everywhere. It is extraordinarily rare to see a capacitive load. Okay. So we have some load, and it is operating at a lagging power factor. And I'm going to call this S old prior to power factor correction. Okay. So as we learned in class Tuesday, the real part of this complex power is the average power. So this is going to be P old. And the imaginary part of this complex power is going to be Q old. And then we will form a power factor angle theta old with respect to the positive real axis, like so. So if I want to increase my power factor or make it closer to 1, what do I need to do to this angle theta old? Do I need to make it larger or do I need to make it smaller?
I mean, if you're assuming 1 means like the whole number integer 1, then theta would need to be smaller.
That's absolutely right. So in order to improve the power factor at which this load operates, we would need to make theta old. So we can do this. One way is stupid, and the other way is the correct way. Okay, so we're going to look at things graphically here. So if I hold Q old to be constant and make P larger, I might have something like this. Right? So I'm just going to do the projection down here. So this would be P new, this would be S new, and this angle would be theta new. The angle is smaller, which means our power factor will be better. However, we have increased the average power consumption of our load. Power factor a few minutes ago, the average power is what we as consumers pay for. So effectively, we would treat this like running up our utility bill in order to avoid paying a fine. Doesn't really make a lot of sense. You know, the math bears out, but from a practical standpoint, this is not the best way to increase our power factor. What would happen if we were able to make Q smaller while keeping P constant? So let's say that we had something like this. So here's our S new. P old is exactly what it was. But now we have this new value of Q. And here is our theta new, right? Theta is smaller. And our average power is the same, which means our utility bill didn't go up. So whatever we're going to do to make this happen is effectively a one-time cost, right? We do whatever this is once to make our reactive power smaller, and then we're good to go. So now we need to figure out how to make our reactive power smaller. So because we're in a circuits class, we are going to consider 3 different cases. What happens if we were to add resistance? What happens if we were to add inductance? And what happens if we were to add capacitance? So what would the complex power supply or absorbed by a resistor look like? So this would be the voltage drop across a resistor times the current flowing through the resistor conjugate. And I'm going to make a little note up here. We know Ohm's law, right? So we know that would be equal So what I'm going to do is I'm going to substitute in a relationship where I'm going to say that I is equal to V over Z, okay? So that we would have the voltage drop across our resistor multiplied by the voltage drop across our resistor divided by the impedance of our resistor conjugate. So that's our complex power. What happens when I multiply a
Could you repeat that? Every now and then you drop out for just a second and I miss something.
Are you there, Dr. Hartman?
Has he been dropping out for you guys too?
I don't know. He's not here no more.
Yeah.
I mean, I think he did say at one time, like, the Wi-Fi in his office is bad. Oh, hey, look, I'm the host now. Oh, never mind.
You back, Dr. Hartman?
Sorry about that. My internet appears.
Yeah, welcome back, Dr. Hartman.
So, all right, let's like sharing. So I don't know if anybody answered my question before I got dropped, so let me repeat it. What happens when I multiply a complex number?
If you're there, you dropped out. You said what happens when you multiply a complex number and then you dropped.
Complex number by its conjugate.
I mean, I know it flips it
So let's
as far as the matrix goes.
let's explore things here, right? So just as a quick aside, let as theta A has the same, but with the opposite sign. So if I multiply A conjugate times magnitude of A squared with an angle of theta A minus theta A, which is nothing more than the magnitude of complex number A squared. By its complex conjugate, I get the square of the magnitude. So using this relationship, I'm going to have the magnitude of the voltage drop across my resistor squared divided by the conjugate of the impedance of my resistor. And because the impedance of a resistor is purely real, this is the same thing as just the magnitude of the voltage drop across my resistor squared. Sorry, and that square should be outside the absolute value sign, divided by my resistance. Can we say about this particular complex power, or the complex power absorbed by a resistor? Is there a J anywhere?
No.
So if there's not a J, then that means it's purely real, right?
Mm, right.
From this, we can see that resistors absorb average power. So that would be what we would include if we wanted to make P old larger. Our first case, which didn't really work out from a practical standpoint. Now let's look at what happens if we have an inductor. Here, so the complex power absorbed by an inductor is going to wind up being the magnitude of the voltage drop across an inductor squared divided by the conjugate of the impedance of an inductor. Well, what's the impedance of an inductor?
One over
Nope.
mu. So then it would be J mu L.
J omega L.
J omega L.
Yep. And because we're doing the conjugate, then it would be negative J omega L. Well, what's 1 over negative J?
J.
Absolutely right. So this would be J times the magnitude of our voltage squared divided by omega L. What can I say about this relationship? So there is a J, there isn't a real part, right? So we only have reactive power here, so that's something. However, the reactive power is positive. So we can say then that inductors absorb reactive power. So if we included more inductance, we would actually make Q larger, which is the opposite of what we are trying to do. So by process of elimination, we probably need to add a capacitor into our system. Let's just see if the math bears out. Okay. So for a capacitor, we are going to have the magnitude of our capacitor voltage squared divided by the impedance of our capacitor conjugate, which is going to be BC squared over negative 1 over j omega c. So I have a factor of negative 1 over j, right? So that's going to look like a positive j in the denominator. So let's do this out. So I'm going to have my voltage squared times omega c divided by j. That is the same as negative j omega c times my voltage squared. So we can see here that whenever we introduce capacitance, it is going to supply reactive power, which is going to make Q smaller because it's adding negative reactive power. So if we were to introduce a capacitance into our system, we would be able to correct the power. This capacitance is important. So I'm going to scroll up here. And I'm going to show you what we would wind up doing. So if we wanted to correct the power with that voltage source. Okay. If we wanted to correct the power factor at which our motor operated, we would put the capacitor in parallel with our motor. So the key here is that we are not going to be changing the voltage supplied by the source in any way because we are putting this element in parallel with it. All right, so talk our way through the process of power factor correction. So specifically here, we understand that we need to introduce capacitance in order to make our reactive power smaller or make the system a little. But how do we choose what capacitor is necessary to correct the power factor to some specific degree? Okay. So our complex power S old is real part P old plus the imaginary part JQ old. And the complex power S new is that same P old plus J Q new. The complex power that needs to be provided by our capacitor the S new minus S old. So this is going to look like P old plus JQ old minus P old plus JQ new. The P olds are going to cancel each other out, and we are just going to have J times Q old. Sorry, I got this backwards. New should go here. Old should go here. Q new minus Q old. Or JQ capacitance. This quantity right here will always be a negative quantity because the whole point of this operation is all reactive power. Okay. So we have this relationship for the complex power being provided by our capacitor. And we also have this relationship for the complex power being provided by a capacitor. So we're literally just going to set them equal to each other. Okay. So we could say is equal to negative RG for C now. And what we'll find is that our capacitor value will be negative Q cap. So negative the reactive power provided by the capacitor, which is itself a negative. Negatives cancel each other out and we wind up getting a positive capacitance divided by omega times the voltage drop across our capacitor squared. Okay. I prefer this one is because we're not able to relate it directly. So instead, what I prefer is this relationship. P old times the tangent of theta old minus the tangent of theta new divided by omega times the voltage drop across our capacitance squared. So let's see what's going on in chat here. I don't know how to improve the connectivity of the internet at my home. You probably have 10 to choose from. All right, so let's look back at that previous example problem where we had a volt RMS source. A 0.01 plus J 0.05 ohm line connected to a motor with an impedance of 8 plus J2 ohms. And we want to correct our power factor to, let's say in part A, a PF new of 0.98 lagging, and B, a PF new of 0.98 leading. And these are actually going to require P old, excuse me, C. Sorry, getting ahead of theta old minus the tangent of theta new divided by omega times the magnitude of the voltage drop across our capacitor squared. And the only other piece of information that I'm going to is operating at a frequency of 60 hertz. Actually, let me put it down here. I'm also going to copy this information. So this is the information about how the voltage source was operating previously. And so we need, okay, the pieces of information that we have. Capacitor in parallel with our voltage source, as I talked about earlier. All right, so I'm not hearing any suggestions, which is fine. So let's go through things step by step. Oh, go for it.
Sorry, I didn't hear you. What, can you ask the question again?
So I want to know what pieces of information we have to plug into our equation and what pieces of information we need to find. Okay, based on the work that we've done already. Do we have P old, which would be the
Okay. Would that be 14.356 degrees? It would be P old?
no. So 14.356 degrees is an angle, so it's definitely not power.
Oh. I was okay. I see. I was answering for theta old. P old.
That day. Okay. Percent correct. Theta old is is 14.356 degrees. Absolutely right there. So I'll put a check by that. P old.
Would that be average or reactive power or neither? Oh, maybe average power?
Yes, because it's P.
Right. Yeah. Yeah. Okay. I lost you again. I heard you confirmed
Which
P.
or
Are you there, Dr. Hartman? Yeah, I think we lost him again.
Yeah.
Yeah, this is
I
this
don't
is
know.
not very good last class.
It's just the ping is high today for whatever reason.
Yeah.
It's usually great.
Oh,
This is the
no.
first time it's ever been like this. Literally, I mean, I've been to every class, and this is not normal.
Hello, hello, hello.
Hey, we hear you.
Okay.
Yeah, we can hear you.
Yeah, I could hear everything that you guys were saying, and I wasn't getting any notification that my internet connection was unstable, so I don't know what was going on. Okay, so let me try this again. Of these 4 different parts of our complex power supplied by our voltage source is P old.
P old would be 18,747.093.
Absolutely right. So it's the real part of our complex power, which is 18,747.093 watts. Okay. So we have this part right here. Theta nu. On that.
Theta nu would be the
So
J part of that. Would it be 4,797.945?
so theta is an angle.
Yes. Yep. You're right. What?
Right.
Oh, you cut out. Sorry. What were you saying?
So because we haven't yet applied our power factor correction, we don't know what yet.
Yeah.
In order to
Okay.
find it, we have to get power factor. So for part A,
Could you say it one more time? You literally like we lost you like 3 times in the last 15 seconds there.
Yeah. So in order to find theta nu, we have to use our new target power factor.
Which would be 0.98 lagging.
Yes, okay. So just as a quick reminder here, our power factor is defined as the cosine of theta s. So that means that theta s is the inverse cosine of our power factor. Does that make sense?
Yes, because you're dividing off the cosine.
Yes, effectively.
Kinda. Or
Yeah.
Yeah.
Yeah. So we are going to have theta nu as the inverse cosine of 0.98, which is going to come out to be 11 0.478 degrees. Now, in part A, we want a power factor of lagging. So should this angle be positive or negative?
Okay, so I look at the chart, I look at lagging. We want it to be lagging, so it would be positive.
Right, so we leave this alone.
Yeah.
For part B, my stylus will write theta nu would be the exact same thing, the inverse cosine of 0.98, but we have to include a negative sign in order to force the angle to be negative. Because the inverse cosine operation on our calculators will only return a positive angle.
Mhm.
So anytime we want to find out a angle for a leading power factor, we have to manually put in the negative sign. Okay, so we now have theta nu. So what about omega? Scroll up here. So we don't have omega, but we can find omega. We were given the linear frequency f is equal to 60 hertz. Omega is simply 2 pi times f, which is going to wind up being 120 pi radians per second. And then our last piece of information is the magnitude of the voltage drop across the capacitor. Do we have that?
Yeah, it's the same thing as BMS.
So what is it?
The 400 angle 0.
So
Or
that's
just
incorrect.
400.
It's just 400 because we only need the magnitude. Absolutely right. So just the 400 volts RMS.
Can the 400 would be like how high that sine wave goes, and then the angle is at which angle it like kind of deviates from its origin. Is that kind of how you think about it?
Yeah, well, yes and no. So the reason why I'm saying yes and no is because we're dealing with an effective value. So this is the DC voltage that would give us the exact same average power as an AC signal that is the square root of 2 times in magnitude of this voltage.
Okay, so it's like a representation. It's not that's not
Yes.
exactly what it described. Okay, got it.
Okay, so we now have everything to plug into our equation. So let's do this really quickly. Let's start with A, right? So I have 18,747.093 times the tangent of 14.356 minus the tangent of 11.478. All of that gets divided by 120 pi times 400 volts squared. And we wind up getting C is equal to, so 16437. Let's see, there are 5 zeros here. So let's call this 16.4, excuse me, 4 zeros there. So 16.437 microfarads would correct our power factor to 0.98 lagging. For part B, we do the exact same thing, except now that 11.478 is going to have a negative sign in front of it. And we wind up getting C is equal to, so I have 142,655, 3 zeros, so 142.655 microfarads. So even though it doesn't seem like it's a big leap to go from power factor of 0.98 lagging to 0.98 leading, it actually requires a significantly larger capacitance to push it past a unity power factor, right? It is possible to overcorrect our power factors, meaning that we could actually make it go beyond the threshold that we wanted, in this case, 0.98, by including too large of a capacitor that would make it be like, 0.95 leading or something like that. So you can absolutely overcorrect your power factor if you're not careful. Generally speaking, your electric utility doesn't care whether or not your power factor is leading or lagging. They just want it to be higher than the threshold they established. All right. Are you guys still able to hear me?
Yeah, if you change something, you've sounded great for the past few. I mean, ever since we had that little pause.
I have changed nothing. I've just been hoping that you could hear me.
That's the internet.
Yep. All right. So I want to work another example problem here. I'm not sure if I put anything like this on your exam, but this is another way to kind of represent circuits, particularly dealing with complex power relationships. So, and I'm 99% sure there's things like this in your homework and in class assignments. So let's say that we have a source. Let's make this 208 angle 0 degrees volts RMS. And let's do it at 60 hertz yet again. And this voltage source is going to supply two loads connected in parallel. And our first load, which I'm drawing as this big box here, draws, let's make it 10 kilowatts at a power factor of 0.8 lagging. And then our second load is going to draw 8 kilovolt amperes at a power factor of 0.95 leading. I want us to determine the following quantities: the complex power absorbed by load number 1, the complex power absorbed by load number 2, the complex power supplied by our voltage source, and the capacitance needed to reach a power factor of 1, where we would put our capacitance here in parallel with our voltage source. Okay. So we're not really doing circuit analysis when we're looking at this. We're simply manipulating our complex power relationships in order to get the information that we need. Okay. So I'm going to write down some review relationships here. The most important ones will be the power factor is, by definition, average power divided by apparent power. And this is also cosine of our power factor angle. And then from this, we actually pretty much have everything that we need. So if I wanted to find the average power absorbed by load 1, let's talk about what I know about load 1, okay? So this 10 kilowatts right here, what does it represent? Average power, apparent power, or reactive power?
Average power?
Average power, because the units are in watts. 100% correct. Okay.
Yes. Yep.
All right. So since we have average power and we have power factor, I believe that we have enough information to find our complex power. Okay. So our complex power, S for load number 1, is going to be our average power P divided by our power factor. That's going to give us the magnitude of S, which is the magnitude of the complex power. And then it's going to have a phase angle of the inverse cosine of our power factor. So if I put this in my calculator, I'm going to have 10,000 divided by 0.8 angle inverse cosine of 0.8. And this gives me, let me write this down. So 10 kilowatts divided by 0.8 with an angle of the inverse cosine of 0.8 gives me 12.5 angle 36.869. So let's call it 870 degrees kVA. Now let's look at load 2. What does this 8 kilovolt amperes represent? Average power, apparent power, or reactive power?
Reactive power, because we're measuring in volt amperes. Wait, that's not right.
That is not right. Volt, excuse me, the units of reactive power are volt amperes reactive. We just have volt amperes. So this must be apparent power.
Yeah. Okay.
So we already have our apparent power and we have the power factor. So once again, we have enough information to find our complex power. So for load 2, this is just going to be our apparent power for load 2 with an angle of the inverse cosine of our power factor, which was 0.95. But because our power factor is leading, what do I need to do to the angle?
Make it negative.
Exactly right. So I just put a negative sign out front here. Actually, let me put this as PF2. So substituting in numbers here, we're going to have 8 kVA. Angle negative inverse cosine of 0.95. Let me put parentheses around this because I'm not sure it worked out just right. I got an angle of effectively -1 degrees, which seems smaller than it should be, but I may be misremembering.
I got 8,000 angle 11.47. and change.
So the 8,000 is obviously correct. For whatever reason right now, oh, because I'm not doing inverse cosine, that's the problem. Sorry about that. Yeah, let me throw that in my calculator. I didn't hit the cosine button enough times.
Can I ask a question just since we're here?
Absolutely.
It might be a little divergent. Sorry if this is an annoying question. How do I know like what mode my calculator needs to be in? Like for instance, when we did the S load number 1, I calculated it out and I was in rectangular mode.
Mhm.
Is that because I don't have a
Your
J?
calculator
I
is-
just how do
So-
I logically know which one I'm looking for? Sorry, go on. My bad.
Well, they're the same thing. So
Yeah.
why does it? It
Yeah,
doesn't
no, I hear you.
particularly matter.
Right. Okay, yeah, that makes sense. Okay, they're just different representations of the same thing.
Exactly right. So
Okay.
I got an angle of negative 18.195 when I do the inverse cosine of 0.95.
Oh, I did 9.8.
Yeah.
5. I get 8,000 angle 18. Yep. And because our calculator can't do it, we have to put in the negative. Got it.
Exactly right.
Okay.
All right, so we've taken care of this part. We've taken care of this part. Now I want the complex power supplied by my voltage source. Well, the easiest way for me to get that is just to say that the complex power supplied by my voltage source must be the complex power absorbed by load number 1 plus the complex power absorbed by load number 2. So this is just Teligent's theorem from the second day of class, right? So if I add these two quantities together, I wind up getting 18,296.995 with an angle of 15.865 degrees volt amperes. And I can express that as 17,600 plus J 5,002.001. So let's just call it J 5,002 volt amperes in rectangular form. So now we're at the last part where we're trying to find the capacitor value needed in order to correct our power factor from whatever it happens to be right now up to a power factor of 1. Okay. So just to rehash that equation, C is equal to P old times the tangent of theta old minus the tangent of theta new divided by omega times the voltage drop across our capacitor squared. So what's P old?
Okay. 10 kilowatts.
So that is the power factor, or excuse me, that's the average power absorbed by load number 1, but that is not the average power that's being supplied by our voltage source, and we're trying to correct the power factor of our voltage source.
P old is 208 angle 0, the whole thing.
Nope.
No.
That is a power, that's voltage.
Is it 17,600?
17,600 watts. Of course. What's theta old?
$15.865 volt amperes.
Degrees, because we're looking for an angle. The volt amperes are really the units of this part over here. I just put the end of the complex. All right. So our goal here is a power factor of 1.
You broke up. I heard our goal here is a power factor of 1.
Yeah, that's the last thing I said.
Oh, okay. Theta nu.
So what angle do I take the cosine of to get 1?
0.
Yep. What's omega going to be?
60
so we were
hertz.
given a linear frequency of 60 hertz. So it's 2 pi times 60 hertz. Radians per second. And then the last, the capacitor, which is, sorry, I scrolled too far. This 208. So we now have everything that we need to plug into our equation. 1,600. 15.865 minus the tangent of 0 divided by 120 pi times 2 squared is going to come out to be 306.672 microfarads. All right, so we have worked example problems today using kind of both forms of our relationships, and by that I mean kind of a straight circuit where we're dealing with impedances and things like that. And now we've worked a circuit where we're dealing with a load that is classified by its average or apparent power and the power factor at which it operates. We have also talked about the concept of power factor correction and why it's necessary, and worked 2 different examples. Everything to be able to do your homework.
You're breaking up again, Dr. Hartman.
Course, is there any questions or anything that I can help you guys with before we get out?
Actually, yeah. Not with this lesson really, but so I'm about to print off like all the old exams and the notes and everything for me to like study with up until test time. And I'm looking on Moodle here, and I don't see the PDF notes for me to download. I only see the lecture links.
We'll go through and I will get those, I'll get those uploaded. If I have been saving them, I guess I've just gotten lax in uploading them. Stuff, so I'll get
Okay,
those uploaded.
When can
At
I
some
expect them
point.
to show up?
Let's call it probably tomorrow morning at the latest. I might be able to get some of them up tonight. The city that I'm in, we're about to undergo a citywide power outage because one of the transformers and the lightning arresters.
You cut off that lightning arrestor.
So there was significant damage to a substation in town. So the city has turned power here in a little bit. So I have to get packed and all that kind of stuff to go somewhere that has utilities so that I can use my CPAP and everything and be able to sleep tonight. So that's my number one priority. After I get that wrapped up, I'll try to get the notes and everything uploaded.
Okay. Sounds good to me.
All righty. Anything else?
And another word for you before I head out. Just actually, do you teach circuits too? Hello?
I do teach circuits 2, and I also will be teaching circuits 3 for the first this fall.
Okay.
Congrats.
Yep.
Yeah.
Finally get to do
All
it.
right. Well, I don't have anything else to ask really, but since this is the last class meeting, I just want to let you know it's been a privilege and an honor, Dr. Hartman. Did you hear me?
Whatever. I feel like I cut out again.
Yes, sir.
Oh
you
yeah,
did.
you cut out again.
I'll be available via email and text all weekend if you need anything.
Okay.
All right.
Appreciate that.
No problem. See you guys later. Sorry about the spotty internet connection.
No,
It's
no
all right.
worries.
I'm sure the YouTube video would be way better.
I don't know about that because it's a
Yeah, 'cause it's
recording
going
of
through
this,
Zoom.
but I do
Mhm.
have all of the old videos and all that kind of stuff uploaded if you need to watch those.
Oh, cool.
Okay.
All right.
Okay.
But yeah,
Thank you. Take
appreciate
care.
it. Yeah, take care, Dr. Hartman. Goodbye.
Later.